This first question is about the Doppler effect. As a car approaches you, its movement causes the waves that you're experiencing to have an increased frequency. It's primarily a frequency effect. Increased as it approaches, decreased as it moves away. So it sounds sort of like "neom" as it's passing by. There is, of course, also a wavelength effect because frequency and wavelength are related inversely to one another. There is no velocity effect. The speed of the wave is based on the medium. That's not changing because of the motion of the object. The amplitude, I would prefer to just say, is not an effect. There's always a slight change in amplitude as you get closer or further away from something. But in terms of the Doppler effect, it's not significant. There's not a noticeable volume change. It's the frequency change that's being described here. In the next question, this image is a lot easier to see in color. You're asked to take a look at this part of the map where there is some green coloring on the left and some red on the left. Based on the fact that the green is associated with increased frequency, that tells us that that portion of that circle has to be moving toward us because the Doppler effect increases the frequency when objects are approaching each other. So basically you've got this motion going on in that section of the circle. The red is a reduced frequency, so that means that this portion is moving away from us because the Doppler effect results in decreased frequencies for things moving away. So what way you interpret that is probably not two formations sliding past each other, but rather a rotational effect. When you have things that are rotating, there's always half of that object rotating in one direction, half in the other, toward and away, and that's what causes that separation that you see there. Question 3 diverges away from the Doppler effect and into the harmonics of pipes. In number 3, we're told that Peter is playing 3 of the open-ended type of pipes, and so we're given 3 different lengths for those tubes. We're given an air temperature and asked to figure out the fundamental frequencies. So there are 3 different calculations here. I'm going to go through one of them with you and then just give you the answers for the other 2. First of all, we have to realize what this temperature means for us. Temperature is related to the speed of the sound wave through the air, and at least in the specific context of this class, the only time we really deal with temperature in this unit is to calculate the speed of the sound wave. So I will remind you of this equation, 331.4 plus 0.6 times the temperature in Celsius will give us the speed of that sound wave, which works out in this case to 340.4 meters per second. And we need that number because the frequency of the harmonics is based in part on the speed of that sound wave. So fundamental frequency means first harmonic. So the n is going to equal 1 in all of these calculations. And that frequency is equal to nv over 2 times the length of the pipe. So this 340 is going to go in for our velocity. 1 is going in for n, which essentially removes that from interest for us. And then these numbers here are going into the length calculation down here. Now there's a slight problem here. Those are given to us in centimeters, so that's a little bit annoying, but we can fix that. Centimeters are 1/100th of a meter, so this is 0.05 meters, 0.065 meters, and 0.085 meters. And then these are the numbers that would go in for L. So let me just show you one. The frequency of the first harmonic, 1 times 340.4 meters per second, divided by 2 times 0.05 meters, and this works out to 3,404 hertz. As we extend the length of those open pipes, we would expect the frequencies to go down, and in fact for the 0.065 you should calculate 2,618 hertz, and for the 0.085, 2002. And again, you're just swapping out the length in this equation for for those new numbers. In this question, we're not given any specific information about length. We're not using our frequency equals NV over 2 or 4L equations here. This is really just asking if you understand the incremental nature of harmonics for these different types of instruments. So you've got an open-ended whirly tube that has a first harmonic of 250 hertz. I'm going to go ahead and write that over here. First harmonic of 250 hertz. And then you have a soda bottle, which is a closed pipe, so it has a bottom that's not open, that has a fundamental frequency of 200 hertz. So I'm going to go ahead and write that over here. And you are asked to find the lowest frequency that is a common harmonic to both pipes. With open-ended pipes, it's fairly simple. As you increase the value of n in the equation, you are really just increasing by multiples of the fundamental frequency. So if we have 250 to start with, the second harmonic is going to be 500, the third is going to be 750, the fourth is going to be 1000, and so on, adding 250 each time. That's for the open pipe. For the closed pipe, it's a little bit more complicated. There are no even numbered harmonics here. So in this particular set, there is no F2 that resonates at 400 hertz. The next highest is the third harmonic, which is 3 times the frequency of the first. And then there's no fourth harmonic, but there is a fifth, and that fifth one is 1000 hertz. The seventh one would be 7 times the fundamental, 1400 hertz, and so on. But we don't have to go that far because we found a frequency that's common to both. That is the lowest frequency that they share as a harmonic. All right, number 5. We're given information about the fourth harmonic for a string. Strings behave like open pipes, so we're going to use the open piped equation here. We're given the frequency of that fourth harmonic as 3,450 hertz, and we're given the velocity, so we don't have to bother with that temperature equation, asked to find length. So this is a frequency equals NV over 2L type of calculation, where we know that the fourth harmonic is 3450, the N is 4, the velocity is 343, and we're solving for length here. You probably want to multiply both sides by 2 to get rid of this guy, and then cross multiply to solve for the length. But the length here works out to be 0.199 meters when you're all done with that. In question 6, we're asked to use information about beat frequencies to figure out the frequency of our unknown bottles B and C here. So what we know is that bottle A is 281 hertz. And we know that bottle B produces 2 beats when played with bottle A. So that gives us 2 choices for bottle B. It could be 2 hertz above bottle A, or it could be 2 below. So those are the 2 options that we have for bottle B. Bottle A and C produce 3 beats. So C is 3 beats away from A, which would make it either 284 or 278. So we took 3 away or added 3 to the frequency of bottle A. We're told that bottle B and C produce 5 beats, so that particular information doesn't really help us because any combination here would produce 5 beats. So what we need to know is this right here, that bottle C is the highest pitched of the 3 instruments. So just subjectively based on their hearing, they said bottle C was the highest pitch, which tells you that it can't be 278 hertz because that would make it lower pitched than 281. Because we also know that B and C produce those 5 beats that earlier we sort of identified as being not helpful, now becomes helpful. Now that we know that C has to be 284, the only option for B that's 5 different is 279, so that eliminates 283 as an option, and those are the three frequencies for those bottles. Lastly, question 7 asks how it is that instruments can play so many different notes if their resonant harmonic frequencies are based on increments. In other words, we set up here in number 4 that this instrument can play this, or this note as resonant frequencies. But what instruments can do in addition to changing their harmonics or octaves essentially, they can change their length. Most instruments have a mechanism by which they can change length, and that's how they are able to adjust all those fine notes in between 200 and 400 hertz, for example. So it's a combination of this relationship of frequency to length and this relationship up here of harmonic increments.